All right, class. Now we are getting into chapter 3 of our A&P class. And so with chapter 3, we still kind of continue on a little bit with some of our chemistry stuff. Although now we're starting to make a transition from the basic chemistry now more into reactions. And that's where we start to utilize different proteins and enzymes. And we'll talk about those here in just a little bit. So when we start looking at this part of chapter 3, we're really looking at energy, chemical reactions, and cellular respiration. That's kind of the crux of this entire chapter. So as we look at energy, one of the things that living organisms require is energy. But what do they require energy for? Well, you'll see this list here, and this obviously isn't necessarily an exhaustive list, but it does show a lot of what our bodies require energy for. Well, one, we require energy for muscle. We have to be able to go through muscle contraction. And so it's basically the way that we power the muscle tissue. We also use it to pump blood, kind of going back to this first section or this first line here. In order to pump blood, we need to have a good heart. In order to pump or utilize the heart, we have to have good muscle. And in order to control the muscle, we have to have energy. Our bodies also require energy to absorb nutrients so that we can create more energy. We need energy for the respiration and exchange of gases, as we see this with our lungs. We need to use it in synthesization of new molecules. So we need to be able to synthesize new molecules within the body so that it can be used in different areas. And then we also need to be able to establish cellular ion concentrations. And we'll talk about a lot of ion concentrations as we get into muscle contraction and action potentials. We'll talk a lot about ion concentrations there. But where do we get a lot of our energy from? Well, probably one of the biggest ways or the biggest locations or substances that we get it from is from glucose. And so essentially glucose is broken down and it's done, or it does this through different metabolic pathways. And by breaking down glucose, this is how we form ATP. And ATP is the energy currency of cells. This is the major type of energy that we will use is ATP. So what is energy in particular? Well, energy is simply put the capacity to do work. Now there are two different classes of energy that we'll really talk about. One is potential energy, and it's going to be stored energy. So it's energy of position. You can kind of look at the name. It has the potential really to do work. Whereas kinetic energy is the energy of motion. So now there are things that are actually moving and being done. So kinetic energy is the energy of motion. Now, both of these can actually be converted from one class to the other. So we can go from potential energy to kinetic energy and vice versa. So let's look at some potential energy in the plasma membrane. Well, when we look at the plasma membrane, there typically is some sort of gradient that exists across the plasma membrane. It oftentimes is a concentration gradient with different ions, but it can also be electrical, where we have a different type of ion across, and it's actually giving us a positive or a negative charge. You'll hear us talk about a resting membrane potential as we get into a little bit more information as we get into later chapters. But that resting membrane potential is typically going to allow the cell or cause the cell to be more negative. And again, we're comparing the boundary between the inside of the cell and the outside of the cell. We also look at potential energy and we look at the energy shells. So again, looking at how electrons are carried out in space of the cell. Remember, if we have a full energy electron or full valence shell in the first level, there are 2 electrons. If we have a full second valence shell level, there are 8 electrons in that second level. So a total of 10 at that point. When we look at the electrons and how they move, then electrons are typically going to move from a higher to a lower energy shell. Okay, so we're moving from a higher energy level to a lower energy level. And kinetic energy can actually be harnessed in these processes to do work. But in order for potential energy to work or to be able to do work, it actually has to be converted from its original potential energy form to its kinetic energy before it can do work. So here's a couple examples here, a couple graphics. Here we have a concentration gradient, again, where we have a very high concentration of sodium and a very low concentration of sodium here. This is outside the cell. This is inside the cell. This is the side of potential energy, where if we don't have significant movement, it's almost as if we're drawing a bow and arrow back, okay? So if you think about as you draw the bow and arrow back and hold it there, it now is no longer moving. So now we have this stored potential energy really in the cables of the bow and arrow. However, once we let go of the cable or the string, now all of a sudden you have the arrow being pushed forward by that cable. And so because of that, that is now kinetic energy. It got transferred from being potential in the held position and released, and now the arrow is moving. And that is a transfer of potential or conversion of potential energy to kinetic energy. And so as these ions now all of a sudden start to flow and rush into the cell for whatever reason may be, that now allows us to have kinetic energy. So what are some other forms of energy? We obviously have potential energy and kinetic energy. Well, chemical energy is actually one form of potential energy, because when we look at chemical energy and you look at a molecule, energy actually gets stored within the chemical bonds. So when we have these covalent bonds between carbon and hydrogen and carbon and nitrogen and carbon and whatever other element we throw out there, there is energy found within those bonds. And so the energy is stored in a molecule's chemical bonds, but then it's released as those bonds are broken. And again, we can use that energy for numerous different things and numerous different functions. Movement, molecule synthesis, and establishing the concentration gradient are all examples of what we would use the chemical energy for. Going back to one of the significant forms or locations of chemical energy is really looking back to ATP and how we have that triphosphate bond and those high energy bonds. When we break those bonds, that is again breaking the molecule chemical bonds. And so that gives us a large release of energy. Now, chemical energy is not present in all chemical bonds. So there are going to be some where there's really not much energy, and if you break them, there's not much released. Molecules that function in chemical energy storage are going to be triglycerides, glucose, and ATP. Those are some of our major ones. Now, what about some kinetic energy forms? Well, you can kind of see this list here. We have electrical energy, mechanical, sound, radiant, heat. All these are different types of energy with different characteristics. So with electrical energy, we have the movement of charged particles. And so these particles actually move, or the ions, which are charged particles, we have the movement of ions across the plasma membrane of a neuron. We can also do this across the plasma membrane of muscle tissue too, okay? And that's going to be electrical energy. We then have mechanical energy. So mechanical energy is exhibited by objects in motion because there's some sort of applied force on them. And this energy is, for example, I should say, muscle contraction. So we have the objects, which basically are going to be bones, are going to be in motion due to the force of the muscle contracting. It shortens and actually puts tension on the bone, and you start to move. We have sound energy, and this is where the molecule is compressed, or the one that is compressed is caused by some sort of vibrating object. So obviously we're going to have sound waves, and as sound waves move through the air, they cause a vibration of the eardrum. And by causing a vibration, you actually send a signal through your auditory nerves into your brain, and that's how you interpret sound. Now, the eardrum is then going to vibrate at different patterns based on the sound waves and based on the pitch, whether it's high pitched, low pitched, what it sounds like. You'll see different wavelengths in the sound waves. And because of that, that then causes the eardrum to vibrate in a different way. We also have radiant energy, and radiant energy is the energy of electromagnetic waves. So basically, we're looking at light. So example would obviously be visible light that strikes the retina. So anything that you see has some sort of wavelength that it's really giving off, and that's kind of the visual wavelength that your eyeball is capable of seeing. As it strikes the retina again, it creates sends the signal to the brain, and the brain is able to create an image. We also have heat, and heat is the energy of electromagnetic waves. Heat is usually not available to do work, but is measured as temperature. Okay. Now, one of the things that we'll see is oftentimes when energy gets converted from one to the other, we'll actually give off heat. We should talk about that here in just a second. If we look at the electromagnetic spectrum, this is really what we're capable of seeing. So this is kind of the wavelength range, okay? And so we have 0.001 nanometers. These would be gamma rays. These are high electromagnetic energy. And these are actually capable of entering the body and damaging a lot of our DNA and essentially causing mutations in the DNA that can eventually lead to a poor production of different proteins or a lack of ability to even create any type of protein. We then get to 1 nanometer and 10 nanometers. You'll see the X-rays fall into that range. UV light falls into that range. But then we get into this very small section in here of 400 nanometers to 740 nanometers. This is the range of visible light. This is the area that our bodies can actually see, okay? And so depending on the wavelength that an object gives off, that indicates the color that our nerves and our brain then will interpret. Once we get outside that, you'll see infrared light and radio waves. The larger they get, obviously the less damaging they're going to be. So then we get into the law of thermodynamics, okay? And the law of thermodynamics itself is the study of energy transformations. We have the first law of thermodynamics, which states that energy can neither be created nor destroyed. It can only change in form. And so what that basically means is energy is energy. It's the amount is there. We just change it and convert it, okay? And so we can kind of see this basically with a lot of light bulbs, especially the older light bulbs. It starts as electrical energy, right? You plug in the light bulb, you turn it on, so you have the electricity coming through the wires. It hits the light bulb. That electrical energy now gets converted to light energy. But because there's a change in energy, whenever there's a change, you often have a discharge of heat. And so that kind of leads us to the second law of thermodynamics. When energy is transformed, some energy is lost to heat. So again, we're having some sort of change. So the energy isn't created or destroyed, it's changing in form. And so now when that light bulb gives off energy, we've now had it converted from electrical energy to light energy, but we have a change in energy or a conversion. So now when you touch that light bulb, you feel heat, okay? And the amount of usable energy really is decreased. So as you convert from one to the next, you start to lose some of that. And you'll see here moving around to warm up on a cold day is obviously one of those examples again of losing heat to energy. And again, as chemical energy converts to mechanical energy, we also then see heat given off. So again, heat is lost when energy is transformed. So now we get into some of our chemical reactions. Now we talked a little bit about some of this, especially with our synthesis and our dehydration reactions and our hydration reactions. We talked a little bit about them, but now we kind of start to go a little bit more in depth with them. So with metabolism, metabolism basically encompasses all biomechanical reactions in living organisms. When we look at the chemical reactions, they occur when chemical bonds in existing molecular structures are broken, or we can have new bonds get formed. Okay, and so we express this then as a chemical equation. And so you're going to see that on one side we have the reactants, and on the other side we have the products. Normally the reactants will be on the left side of the yield sign, which the yield sign, normally you'll see this isn't going to be overly fancy art, but the yield sign normally is an arrow. And so you have your reactants on one side, on the left-hand side here. So our reactants would be there. Our products would end up being there. Okay? And so again, we express this as a chemical equation. We start with something, we go through the reaction, we get something. So let's look at the reactants first. The reactants are going to be the substances that are present prior to the start of the chemical reaction, and they're going to be written on the left side of the equation. Our products are going to be the other ones. They're going to be on the right side of the equation, and these are the substances that are formed from the reaction. So you'll see here's that yields arrow that I referenced before, right there. You'll have your reactants, which are A in this case and B. So we take A plus B, and then we get the product. We get C. And so again, this arrow, this yield sign, indicates the reaction direction. So it's telling us that it's moving from this direction to this direction. Now, in a balanced equation, the number of elements are equal on both sides of the reaction. So, if we have so many molecules of water, we're going to be able to find in some way, shape, or form, if we have to convert them, the same number of hydrogen atoms and the same number of oxygen atoms that we started with on this particular side, depending on the type of reaction. So if we look at the reactions, we classify them based on 3 criteria. We have 1, the changes in chemical structure. 2, we classify them based on the changes in chemical energy. And 3, we classify them whether the reaction is irreversible or reversible. So let's look at the chemical structure first. So when we look at the changes in chemical structure, we're looking at how things actually transition chemically. So we have a decomposition reaction, which basically breaks things down, a synthesis reaction, which puts things together, and an exchange reaction, where we have one section that exchanges with another section. So if we look at a decomposition reaction, we have an initial large molecule that actually gets broken down into smaller structures. So again, here's our reactant, which is AB. This yields arrow indicates that we're moving in this direction, which gives us A plus B. This would oftentimes be a hydrolysis reaction, in which our example here is going to be sucrose. So sucrose is a combination of both glucose and fructose. So if we go through hydrolysis, we're adding water, and so we are going through a decomposition, or in this particular case, a more specific reaction called hydrolysis. But again, we are breaking down a molecule into component parts. What we'll find is that all decomposition reactions in the body are going to be referred to as catabolism, or a catabolic reaction. So if we look down here in a decomposition reaction where we're breaking things down, or in this case specifically a hydrolysis reaction because of the water here, you see that we have sucrose. We add water, so water is actually going to be added to this ester bond, okay? So now we have glucose, which, again, I said this is where we're adding the water molecule to, okay? So here we have the oxygen of 1 and the OH, or I should say the oxygen of one part of the water molecule and the OH of the other. And so you take this, again, we've done this before, you take this particular hydrogen and you take this particular OH, and that's where we get our water from, okay? So this is, again, a decompositional reaction, or more specifically for this one, a hydrolysis reaction, where we're adding water to the system. Now, in this one, we have a synthesis reaction. A synthesis reaction is where we have 2 or more structures combined to form a larger structure. So here we're taking our reactants, which are going to be simple reactants, A plus B, and this gives us AB. This is going to be called a dehydration synthesis reaction because of what you see down at the bottom. We are now releasing water. So dehydration synthesis reaction is forming a dipeptide in this case. We call these anabolic reactions or anabolism. And it's the collective term for the synthesis reactions in the body. Again, here we take our amino acids, we join the H of one group, the OH of another group, and that gives off water, and that forms here our dipeptide bond. Our last one is going to be an exchange reaction. And in this case, the groups actually exchange between 2 chemical structures. It has both decomposition and synthesis components. And this is the most prevalent type of reaction in the body, okay? Where we basically have our reactants here, and essentially what you see is that the B and the C, or I should say, the B really switches places, and then we get A and BC. So we kind of are exchanging one location to the other. And this is what we see in the production of ATP in muscle tissue. So for example, if we take the process known as direct phosphorylation, we take creatine phosphate, which has a phosphate group on it, and we have ADP, which is adenosine diphosphate. So we take the phosphate group, we add it to ADP, and now we have just plain old creatine with ATP, okay? So again, taking a phosphate group, adding it to ADP, leaving us with creatine and ATP. So as we now move on to a different way of classifying changes, we're now looking at how we see changes with chemical energy. And this is a different classification. So with exergonic reactions, the reactants have more energy within their chemical bonds than what the products do. So what that means is that energy is then released with a net decrease in potential energy. For example, decomposition reactions. We have more energy in the initial bonds than what we do the formed bonds, okay? Or the bonds that are still remaining, as the case may be. With endergonic reactions, the reactants now have less energy within their chemical bonds than the products. So now we're typically going to see a net increase in potential energy. So now we're actually forming bonds. This is where we see a synthesis reaction, where we actually form a bond. So a dehydration reaction where we actually pull water out and form a bond between 2 different molecules. So this is kind of what we look at as far as the graphs go when we look at the reactions. Here we have the reactants at point A. This is kind of level 0 going straight across. Here we have energy is supplied. Here we have energy is released. So with an exergonic reaction, we see what some of our reactions or our reactants could be. Here we have a situation where energy is released. And so we're breaking down bonds, releasing energy. And so now we have less energy than what we started with. In an endergonic reaction, we have our starting point here. We'll say we have amino acids as our example. Now we're actually forming bonds. We're creating a peptide or a large macromolecule. And so now we have more energy in those bonds than what we started with. So as we start looking at some of our chemical reactions or continue with that, and we look at ATP cycling, ATP cycling is this continuous formation and breakdown of ATP. So ATP is going to be formed when energy is released in our exergonic reactions, okay? So the fuel molecules from food are then oxidized, and the energy in their bonds are transferred to ADP and free phosphate to form ATP. The ATP is then oxidized to aid endergonic reactions. Energy is released from ATP hydrolysis, and this provides us the energy. And normally within our entire bodies, we really only have a few seconds worth of ATP present at any given time. And so therefore, because of that, we are constantly going through the formation of ATP continuously in order to provide us with energy. And so to kind of put this in graphical representation, you'll kind of see this little flow chart. You'll notice that it's just a continuous cycle, okay? We really can kind of pick up at any point, but if we look here, we have energy supplied. So now we have ATP, okay? So now we're going to break down ATP because we need energy. So now we go through an exergonic reaction, we release energy, and we now have an inorganic phosphate group. Because again, we had to break this high energy bond to get the energy. So we broke that bond. We're left with ADP, an inorganic phosphate. But we did release some energy. So now we go through this process where we now form ATP. So now we take ADP, add one additional inorganic phosphate, we add energy to the system, and now we're back to having a high energy bond with ATP. And then the cycle just continues and continues and continues. And that's how we are able to continuously supply ourselves with ATP. We also have to look at classifying reactions as irreversible or reversible. So with an irreversible reaction, we have a net loss of reactants and a net gain in products, okay? So we have A plus B yields AB, or AB yields A plus B, okay? But again, we have a net loss of them. With a reversible reaction, the reaction does not only proceed to the right, it can actually proceed both directions. So we have no net change in concentration of either reactants or the products. And this gives us equilibrium, okay? And so this is where you see the double arrow. Whereas in an irreversible reaction, we're basically saying we have the reactants, we go through the reaction, we get the products. With a reversible reaction, we constantly see kind of this equilibrium of flowing back and forth, where we have the reaction going one direction, so A plus B equals AB, but at the same time, we also have AB being broken down back into A plus B. So there's a constant change, okay? Now, if we happen to change something within this equation, we can drive the reaction one direction. So if we increase the reactants or decrease the products, so increase the reactants or decrease the products, it actually can drive the equation to the right. So we add more of this, or we take away some of this, it's going to force that equation or force the equation this direction. We also have the reverse is true. If we decrease the reactants over here or add more of the product, we can actually drive that reaction going more to the left. Okay, so that's just a few ways of classifying our chemical reactions. And this will actually be a nice place to pick up, going back into or moving into our enzymes as we finish up chapter 3. Not overly long, but why don't we just do this? Why don't we use our code word for today for this section as ATP? Okay, I think that'll be a really good one. Again, the code word for this chapter 3 part 1 is going to be ATP. Again, I think that'll be a really good one to just indicate this section of our notes. Otherwise, have a good rest of the day.